Okay, so good morning. So, as Felix said, I don't speak German, so I'm sorry. So if you don't understand because of my English, or if you have any question, ask the question directly and don't wait until the end of the presentation. Okay, so we'll talk about image quality today. So how to check the image quality of your scanner or of your camera, of your scanning device, and how to check that, not looking at the image, but using charts and numbers. So we'll have a look rapidly about how a scanner is made, how it works, what is inside a little bit. We'll see what are the criteria for the quality. What do we have to check on an image to say it's a good image or not. We'll see some standards, because once you know which criteria you have to check, you have to know how to measure this criteria, you have to know which value you should reach, and there are some standards for that. And then we'll see how to use the chart, what chart to use, how to use it, how to calibrate the scanner rapidly, and then really how to make the quality control, first on the screen and in the afternoon on the scanner directly. Okay, first introduction. I guess you know this painting, but as you can see, all these images, it's a real search on the internet, all these images are quite different. So first thing we can say, there is only one painting and there are different images. So that means there is something to do. It's not good. What we would like is when you scan one document, you have images which look the same. If we go further, which image do you think is the worst, the bad one?
Second from the right side.
This one here? Yeah. Obviously, this one is too much green. Okay. But what do you think about this one?
The black is too strong.
Yes, black is really dark. Black is really dark, and if you look here, you can see the arm of the chair. Here you cannot see it. Here, on my screen you can see it. It depends on the screen. Here it's difficult, but on this one really you cannot see it. What does it mean? This image here is too much green. But if when you scan the painting, you scan also a color chart at the same time with the same setting, you have a chance to be able to correct, because you know the value of the chart. You don't know the value of the painting, but you know. So you have a chance to correct, to build an IC profile and to correct the image. It's not the best, but it's possible. This one, the information is lost. So that means it's too late. You have to come back to Paris and scan it again. So that means, what we can say about that is the most important is what we call the tonal scale. The gray level, the level has to be at the right level, especially in the dark area and in the white area. We could lose some information. That's the most important. The color will come next, and usually it will not be a big problem. So another introduction. Maybe you know already, but you see this square A and this square B. Do you think they have the same level, the same color? Yes, no? Obviously not. This one is a white square, and this one is a gray square.
It doesn't look like, but it's brown.
Yeah, but of course, if you do this, you can see they have exactly the same level. So what does it mean? It means that when we look at the image, this kind of image, we have an image processing in our brain, and we are trying to compensate, because we can see there is a shadow here, and we know that inside the shadow, because of the shadow, the white will be darker and so we compensate for this. We can see there are some dark square here, so we say this one is white, a little bit like this one, and this one is obviously gray. So what does it mean? We should not trust our eye too much when checking the image, especially on levels and on color also. On color it's obvious. And that's why we would like to prefer using charts and getting numbers from the chart. Here, if you check the numbers, this one is 120, this one is 120 also. So you can really, you are sure they're exactly at the same level. Okay, so that's why we really want to do this as much as possible. It's not always possible, but we want to use charts and get some numbers from the chart. That means we will not look at the image too much. There will be an image quality control by eye, but here what we want to do is just look at the numbers. So it doesn't matter who is making the control, because some people may think this image is too much green, the other one will think it's too much yellow. It doesn't depend on the viewing condition. So the light in the room, the light on the screen, you can see maybe these two screens are quite different. Okay, and even if it's calibrated. And having numbers also that allow to set some limit, to say above this limit, it's okay, under this limit, I don't agree. This image has to be made again. And once we do that, of course, we will use standard, because it's not good if each library use its own tolerances. It's better if everyone has the same. So there are some standards for that. And we will look at the image, I mean, I should say on the disk. We don't care about how the image will be displayed. This is another step. And we'll try to have an image close to the object, to the document, rather than being nice to display. That's something else. That means we'll have a master image as good as possible, and then this image can be modified to be displayed. But there are some limits on that. The main limit we will see is the spectral response of some documents regarding the chart. That will make some difference sometime. We will also calibrate on the chart and use the same chart to check. So it's maybe not the best way to do, because we will not scan chart at the end, we'll scan documents, so it's different. There are some trouble sometimes with the charts accuracy. The charts are not perfect. You will still need a visual check for artifact, like, I don't know, bad pixel on one corner or something we cannot detect by the charts. And it will be difficult to apply on some document, like gold leaf painting with 3D, everything. Okay. So, how a scanner is made? So there are two main kind of scanner. We have matrix scanner, like this one, and line scan scanner, like this one. A line scan scanner can see only a line and will scan the document. It will move over the document to make the image, like a flatbed scanner in your office. Matrix scanner is like a photo camera. It will take a picture. So all the sensor will see the image at the same time. There will be no movement. But to make the color image, we need three information: red, green, and blue. And not the only way, but the most time, people will use one filter per pixel. So you will have a green filter on one pixel, a red filter on the next one. That means to get for this pixel here, to get the green information, I have to get it from the neighbors, and the same for the red information. And that is not perfect. The exposure time, so the time to get the image, is usually about 100 milliseconds. So that's quite fast. But for camera it's quite long, so we don't need so much light. Low light is enough. I mean, here the light is off, but you will see it's not very strong. The total scan time is equal to the exposure time. That means it is very fast. It means the document has no time to move, and you can be productive. You can scan very fast with this kind of scanner. And there are no movement on the cameras. That means Scanner will be usually smaller, cheaper, easier to move, and more convenient. To make the exposure, we need to have a shutter. That is something that will block the light. So the light will be took from one time to the other time during a certain amount of time. Some camera has a mechanical shutter. The mechanical shutter will have a lifetime which is limited. Some camera will have a rolling shutter. That means these pixels here are not exposed at the same time than this one or this one. So this is not a big issue when scanning something which doesn't move. You can see it only when you have something moving very, very fast like this. But it could be visible when you are using a flash. The flash is very short also. And then you could have some black pixel here and black pixels there because they are not exposed at the same time. Not a big problem. Line scan scanner. So we have one here. You have a camera looking here with 3 lines. One again for each color. And we will scan a document. That means we'll have, for each pixel, we will have the 3 red, green, and blue information, which is better. So we don't need to have any image processing to get the color from the neighbor's pixel. We have really to scan the document, so we need to move something. That means the scanner will be more heavy, more slow also. The exposure time of one line is quite short, but 1 millisecond. That means you need a very strong light. So very strong light can be good sometimes because it doesn't depend on the ambient light. You will see a difference on this one. But the total amount of light on the document stays very low because the light effect is cumulative. That is, if you send a very strong light for a very short time, it's nothing compared to having a book exposed here for 1 week. It's nothing. So the scan time now will be the exposure time multiplied by the number of lines. And the number of lines can be quite high, can be 10,000 lines. That means the scan time will be around 10 seconds. I mean, we have an exposure time which is 100 times smaller than on matrix scanner, but the scan time is 100 times higher. So less productivity. But with that, we can build very large images. So scanning, for example, A0 at 600 dpi, we can do nearly 2 GB image in one scan, which is big. We cannot do that yet with a matrix camera. Maybe in the future, but not yet. There is something special on line scan scanner. The 2 axes, I mean, the scanning direction and the, let's say, camera direction are a little bit different. They're not the same. If you scan a book like this, and the book is there, and the book is not flat, you will see the curvature at the top and at the bottom, because the camera is looking like this. Or like that, you can see the curvature. If you rotate the book or if you scan like that, I mean being above the book, not doing it like this, but being above the book, the camera will be always here at the vertical position of this line. That means you will see something quite different. Here the red thing is hidden, the cover is hidden by the page. When you scan like this, you can see it. That means the image will be different from an image made by a matrix scanner. And by the way, here you will have no curvature correction, no curvature. So it can be good, can be not good sometimes. And so this is not really scanning, but just to show you, we can use line scan camera for different purposes, like photo finish in sport, for example. Here you have one camera, one line looking at the arrival line, and you have the people running in front of that. And if you put your foot on the line, the foot stays a long time, so it is quite long. And at the opposite, if the foot doesn't go on the line, the foot goes faster than the runner, so the foot is very short. Okay. So what does it mean? When you scan something, it should not move at all. If not, it will be distorted. So these are the two kinds of scanner. You have some other parameter. When you build a scanner, you have to take care about the lighting. We'll see the spectrum of the lighting is important. All the shadows, the reflection you can get also is important. Technology also, depending which color filter you are using, which are using CCD or CMOS technology, the size of the pixel, everything can have an effect at the end of on the image quality. The optics, especially the resolution, is very important. Of course, electronic, you will have more and more image processing in scanner now, in camera. If you look the size of your camera here, it's very, very small. So the pixel receive not a big amount of light. So the signal is not very good directly from the sensor. So you need a lot of image processing to correct that. And it's less on this kind of scanner, but a little bit also, you'll have more and more image processing. So let's talk about lighting. These two lighting here are from fluorescent tubes, we were using in the past. So this one, they have both the same color, because when you look at the lighting like this, with the camera or with your eyes, you will divide all this light in three parts, the red, green and blue parts, and that's it. That means from all this information, you will get only three values: how much green, how much red, how much blue do I get. And if you compare these two, the amount of blue, green and red are the same on these two lighting. So they have the same color. You cannot make the difference between these two lighting when you look at the lighting. But you can see that here there is a big difference between this frequency and this one. Here you have nearly no light, here you have a lot of light. On this one it is more smooth, that means there is less difference between two frequencies. So what will happen with that? If you look at a white page which sends back all the light that is coming on, it will make no difference. If you look at an object which is reflecting, for example, a lot the light in this frequency, with this lighting, this light, you will have not so much light. On this one, you will have a little bit more. So the color of this object will not be the same if you use this lighting on this one. So these lighting have a parameter which is the color rendering index. On this one, it is not very good, so it is 80 only. On this one, it is better, so it is 90. The best is 100. The daylight is 100, for example, because there is no difference. It's not flat, but there is no difference between two frequencies. So it's good. It's better to have the highest possible rendering index. Today we don't use these fluorescent tubes anymore. We are using LED, but it's the same on LED. This LED, you see there is a big difference here between this frequency and this one. So the index is about 80. On this one, they have improved the spectrum, so the index is about 90. And maybe in the future, we'll have an index of 100, which will be much better. So that can make a difference sometime on some document. This is the spectrum of the filter on the camera. So on our eye, it's about the same. So when you look at one lighting, you look how much blue do I get. So you make the amount of light you get with this filter. So it will be in this area here. You would say how much green do I have? So here somewhere. And how much red do I have? And again, you get only three values from all this information. This is this chart. you know this chart probably. This is the reflection spectrum of the grayscale. So you have the white patch, the gray patch, and the black patch here. And you can see there is no difference depending on the frequency. It's completely flat, I mean, except a little bit in the real blue. That means when you look at this chart, you will have no difference when you use this lighting on, or this one. But if you look at something like this, you have two lights. So light B is something, doesn't exist really, but a straight line, having the same amount of light on all frequencies. And this light here, light A, has the same amount of blue. You see here I have more or less the same amount of blue, same amount of green, and same amount of red. But it's not stable. You have some difference between this frequency and this one, for example. So if you look at this object, this is a reflection spectrum of one object. You can see that this here, it will send a lot of light in this frequency, and it's in front of this one. So that means if you will multiply this spectrum by this one, you get that. So with a flat light, you get with the red curve exactly the same curve than this one. But if you use the blue lighting here, I mean blue curve, you will see you will have more light in the red area. Here it will be about the same. So if you look in the blue area, you have more or less the same amount of light with both lighting. Here it's about the same, but here we have more light with this light here. And if we check the value, you see the blue value are about the same, the green value are very close, but there is a large difference on the red one. So the color you will get are this one. So on the same object, it will appear yellow with this light here, this one, and it will appear more red with this light, because of the two spectrum of the light and the object. So that's what we call the metaremerism. So an object can have a different aspect depending on the lighting spectrum. And this can be a problem on some time. I have seen that, for example, one day, you calibrate your scanner with two different lighting, or you have two different scanners. On the chart, you get exactly the same value, but the document appears completely different depending on the lighting you are using. So your calibration is right. You cannot have any difference on the chart, because the chart has a very flat reflection spectrum. But on the object, you have a huge difference. And there is no real way to manage that. I mean, we'll see at the end. We can only modify a little bit the ICC profile, or when it's possible, we can change the lighting. So changing the lighting will be more easy on a matrix scanner, because we don't need a lot of light, so you can pick up any light you want. On this one, you have really to change it. I mean, only the manufacturer can change the light on that. It's okay for that? Okay. Talking about light, of course, the angle of the lighting is also important when you scan something which is not flat. Probably better to have the light on the side for this kind of document. And if we have time, we'll show you. You can also use the lighting to remove some reflection. Using both lighting selection and vivid image processing, you can scan a very bright document or a document within a plastic mylar and completely have no reflection. Yeah, I can show you on this one, not on this one. And the lens, we're talking about the lens. The resolution of the lens can be a weak point. Here you have two lenses. These curves are given by the manufacturer. So what it is, here you have the center of the image. This is the edge. So the image is 42 millimeter. Okay. And the same for this one, center and edges. So both are making the same size of image. On this one, you have the contrast here given for different frequency. So this is a high frequency and this is a low frequency. So you can see what at the low frequency you have the maximum contrast in the center and in the edge. So it's perfect. When you increase the frequency, the contrast is dropping a little bit, but there is not so much difference between the center and the corner of the image. That means it's a good lens. On this one, you have only two frequencies, so 10 and 30 per line per millimeter. So in the center it's quite good also, but you can see that on the edge it is dropping a lot. On the blue curve here, so at this frequency here, on the edge, you have only 10% contrast, which is quite low. And that means on this image, with this lens, the image will be good in the center and will be a little bit blurred on the edge. And this, it depends, of course, it depends on the lens, so it depends on the manufacturer of the scanner. You have to select the best possible lens. Let's talk now about theory. So gamma correction. Do you know about gamma correction? Yeah. Okay. So at the beginning, when people made the first images for TV, you know, they were using this big CRT tubes screen, and this screen has this kind of response curve. That means you send a signal here on the screen, and at the beginning you get nearly no light, and at the end you get much more light. It's not a linear curve. But at this time, the camera was made with a tube also. And as it was working in the other way, the curve was the opposite here. So if you take a picture with that, and you display with this one, the final result is this. So you have the same contrast when you look at the object or when you look at the screen. So it's perfect, you have nothing to do. And then came CCD camera. CCD camera has a straight line here. So if you take an image with a straight line and you display with that, the result will be like the red curve. So all the dark area will be too dark. So we need in CCD camera to compensate for that. So we need to apply this curve here to compensate for the display. So that means we have to amplify all the dark area. And you will see there is some effect on the noise especially. So it's called gamma because the formula is y equal x power gamma, and gamma for the red curve is about 2.2. And of course for the camera it has to be the opposite, so 0.45. And but that's not the only reason. If we look again at this chart, you have the black patch, white patch, and the gray patches. Between these two, for you, which one is the middle gray? That in between white and black. Is it the left or the right one? The left one, yeah. Okay. The left one. So this is based only on our vision. It's not, you cannot measure it like that. The camera will say the average one is probably this one. Or maybe between these two. I don't know. But we see this one as a middle gray. You know. And if you check how much light it is sending back, it is only 18%. Not a lot, only 18% of light. And it is logical that this gray level, which is for us, it is the middle gray, on the image, it is logical that it has a middle value between 0 and 255. And that's why it is still interesting to keep this gamma correction, because on the disk you will have no display, so you will have this curve. The image you store is like that. So it is good if the middle gray has the middle value. That's why also we are applying this gamma correction. And you can see here, this is a 2.2 curve, and the green one is supposed to be the one of our vision. It's called L star. So you can see they are very close together, and not a lot difference. Some people are also using 1.8, which is a little bit lower, but still okay. But you will never use this one, which is a linear curve. And you will see that this, depending on the color space you are using, you will have a different gamma correction, different curve. So on a chart, usually we know first the manufacturer will give the density of the patches. What is density? It is if the patch sends 100% of the light, like this, more or less, you get a reflection of 100, so density is 0. If the patch sends only 10%, you will have density 1. If the patch sends 1%, it will be density 2, and so on. So it's going very fast. This one will send about 3%, I think. So it's density 1.5, between this one and this one. Density 4 is very, very dark. On a printed book, usually you cannot have something darker than that. That means on a book you will have a density from 0 to 1.5. And this is only on transparent document or maybe some painting or you have very dark black. And once you know this, so you know the density, this is again the same chart. Once you know the density, you can calculate the reflection with this formula. And then if you know which gamma correction you are using, you know which value you should reach. So it's not random, you don't do what you want. This should not be 0, it should not be 20 or 40. If the gamma correction is 2.2, it will be 54. If the gamma correction is 1.8, it will be 32. So it's quite different. 54 and 32 are not the same level. So here you know exactly which value you have to reach on the chart on the grayscale. It depends only on the gamma correction you are applying. So here I have 1.8, 2.2, L star, and this is L level. Usually when you do L level, it's from 0 to 100, so that's why the number is different, but these two curves are the same. Okay, most people are using this one. So, yeah, it comes, from that. You know Adobe 98 color space, maybe? It's a color space coming from Adobe. So it's from 20 years old already. And the gamma correction is 2.2. You have also sRGB, which is designed to be displayed on any screen. You know, when you take a picture, you send it on the internet, you don't know on which screen it will be displayed. So you have to put it in a color space which is small enough to be displayed on any screen. It has also a gamma close to 2.2. This one we will use for calibration as a L star curve. And you have some other having a gamma 1.8. So depending on your color space, you know which gamma you have and then which value you should get. Then we're talking only about grayscale. Any question on this gamma correction? No? Okay. Now we'll talk about color. So we know that to get a color we need 3 values, red, green and blue. And these 3 values come from the filter which is on the camera or which is on the screen if we want to display an image. It's the same. This screen has some red, green and blue filter also. So if you take this filter, red, green and blue, here you can display all the colors which are inside the triangle, not the one which are outside. Display or scan, it depends if you have a scanner or a screen. You can see that sRGB is quite small. So this color will not be inside sRGB, so it will be described probably like this one. And if you take this color here, you see it at the limit of the sRGB color space. So you guess that in this color space, the value of this green will be 250 or close to the limit. But if you take the same color in this color space here, you see it's, let's say, at the half of the maximum value. So the value for this green in this color space will not be 250, but maybe 130. So that means we'll have completely different value for the same color, depending on in which color space we are. And that is the main problem of RGB world. That means if you scan this red patch, you don't know which value you will get. You must get. You know it only if you know in which color space you will be. So if you go to sRGB, I don't know the value, you will have some value. If you go to Adobe, the value will be different. So all time you have to know in which color space you are. And you have to translate sometime from one color space to the other one. And there is another issue. It is that we are less sensitive to any change in this area compared to this one. So if you say, I have a color and say +10 on the blue channel in this area, you will not see the difference. If you do it here or there, you will see the difference. That means we cannot make some measurement in this color space, because if we want to say, I allow to have a color of 10, it will not have the same effect if it's a green color, a blue color, or a red color. So it's not easy to make any measurement in that. Because of this, they have created what it is. The LAB color space. The LAB color space, what it is, you have luminance from black to white, and you have the middle gray, which is here. It's a gray 18%. And you have one axis going from green to red, and another one going from yellow to blue. And this color space doesn't depend on the camera you are using on the screen. It's independent from the device. And it has been made so that any change, the same amount of change in a color will have the same effect if the color is this one, this one, this one, or this one, anywhere in the color space. If I come back on sRGB, this is again my chart. You have all the value for Adobe, Apple, Profoto, and sRGB color space. So if we zoom in, you can see first the black is really about 54 for Adobe. It's about the same for sRGB, but you can see that in Apple or Profoto, it is about 30, because the gamma is 1.8. You have not so much change in the white area, because the gamma curve are finishing at the same level, you know. If you come back here, there's not so much difference between the three curves. Here you have much more. And if you take the yellow patch, you will see between these two, you have a big difference. You can see its value are usually higher with sRGB because the color space is smaller. And you can see that this blue here is not inside sRGB. It is a little bit outside. Here's the value, the real value is negative. So it's a little bit outside. So it's a small color space. It's okay for most of the document, but it's still reduced. This one is wider. Okay for that? So each color depends on the color space you are using in RGB. That means we will always translate the value in LAB to make any measure on the image. And what is that? So we talk about color space and ICC profile. It is exactly the same. So you will need to know the profile or the color space of your scanner, because you need to know for this red which value I will get from my scanner. And it will not be the same for both scanners. So if you want to get the same image, you need to translate to an output profile. And this translation is really a translation. It's like this scanner is speaking French, this one is speaking Spanish, and you want the text in English. It's exactly the same. So you take the value from this scanner, you have the table, the color space, and you translate to get the value of the red patch from the color space of the scanner to Adobe or sRGB or anything else. That's how it works. And each time you go through LAB because it's a reference. And that means the value, the RGB value will change if you take the raw image of the scanner and the output in Adobe 98, you will not get the same value. Okay, so now let's talk about criteria. So there are 6 main criteria to check the image quality. So I want you to tell me which has this criteria. So what do you check in an image to say the image is good or not good? Yes, resolution, so it will be inside the resolution, so it's sharp enough, yeah? The color, yeah, you can have, I mean, it will be in both criteria, you will have the tonal scale and the color. It's we split in 2 different criteria, okay? Then, 3 again. So we check the resolution, the color, the gray level.
The colors are the same.
Yeah, it's the color accuracy, yeah, it's the color accuracy. The 3 other are more some problem you can meet. This is a tonal scale. Eh? Sorry? Contrast will be in the tonal scale more or less and the resolution, but what can go wrong in an image? Yeah, we're talking about lens. If you have a bad lens, what can you get? If you scan a chart like this one having some square. Distortion. Distortion, yeah. So the square may not be a square. So it's a geometric distortion. So still 2 other. Something similar to the geometric distortion, but about the light level. If you scan, and for example, look at this. Yeah. Sorry, as it is here. I mean, sorry. So here the light is off, but you can see there is really a problem here. So you have more light here than there. So it's a lighting uniformity. Now you have to check this. And the last one, that means it's not a problem for you. I mean, that means you have a good scanner on that. Today is no more a big problem, but it has to be checked. No, it's not really. We are scanning charts. No, it's the noise inside the image. You can have noise inside the image, and you have to check it. So here we have. So there is no real order. This one is very important. This one, of course, but this one, I mean, are not important if they are okay. If it's very bad, if you have a huge amount of noise, or if you have a very bad uniformity, you cannot scan also. So you have to check all this. So we'll check all that with some charts. Of course, there are some sub-criteria, especially on the resolution. And this we can check with charts. We still have to look for artifact, like a bad pixel, some stripe that doesn't appear in these numbers. Anything strange in the image. If the document is moving when you are scanning, for example, something like that. So because of that, we still need to check the image by eye. But we try to get as much as possible some numbers to say it's good or not good. So tonal reproduction. This one is very easy to understand. You have a grayscale, could be this one. You have different gray from black to white. And here you have, so you scan the image, you get the image, you run specific software, and you compare. This is the reference value from the chart. This is supposed to be 240 and so and so. And you compare with the image from your image, the result from your image. And it should be a straight line if the value are the same. So there is a tolerance. Here we're checking metamorphose, so the delta L allow these two. That means you have to be inside the green area. Maybe the yellow area is something wider, a lower image quality level. So as long as you are inside the green channel, it's okay. If you have too much light, the level will be here. You will have to reduce the light or the exposure time. If your gamma correction is not the right one, the middle will be too high or too low, so you will have to correct that. And if your black level is not correctly adjusted, the curve will be too low or too high. Okay. So quite easy to understand, not so easy to reach, but easy to understand. Inside that, you may have the curve doing like this, like that. So this is not very good. For example, here we have too much contrast between these two patches. We have too much difference, so too much contrast. Here we don't have enough. So we can be within the green area, but still have a bad, not so good image because what they call the gain modulation, it's the slope of the curve, in fact, is not stable. If the curve is not straight, it's not very good. So this is measuring the slope between two patches. So like this, so you have the reference value, you have the sample value, so the value of your image, and you apply this formula, and here you get, for example, 108, a bit more than 108 between this value and this one, this patch and this patch, which is too high, usually. But you can also calculate between 1 and 3. In this case, you will have a more smooth result, more stable result. For color accuracy, again, we don't want to look at the image because it has to be possible, but it's quite difficult. It's much more stable if you do it with a chart. So you scan a chart. It can be this one. It can be also this one, which is used maybe more often. And here we have 24 patches. So you have 24 value here. So here you display the value from the chart and the value you get from your image. And you compare both. So we are in LAB color space because that's the only way we can measure the color accuracy. And here it's not a space, it's just, you can see that all the grayscale here is at the same point. The luminance is in this direction. Okay. But the software is measuring in the space. And if you have a difference between the value of the chart and the value of the camera, you have a distance in the color space, which is called delta E. And here we have only 24 patches. On this one, there is more than 100. So to check the result, we'll take the average value. Average delta E should be lower than 4 or 5. And we'll take the maximum one. Maximum should be lower than 10, 15, 18, it depends. And then we can say if the color is right or not. Without looking at the image. So just its numbers on the disk. It doesn't depend on the display, it doesn't depend on the light. This is the formula, sorry for this, but the delta E, we'll see there is some other formula we'll see later. This is just the distance between 2 points in the color space. That's the issue. And we'll talk about the delta L, it's just the difference on the luminance. Any question on colors? No? So let's go to resolution now. So inside the resolution criterion, you have what we call the sampling efficiency. Because here we are scanning a chart. It is this one, maybe you know, we can circulate. It's a chart having lines, very small lines. And here we are looking at the number 11. It starts at 1. That means 1 pair of line per millimeter. That means you have 1 black line, 1 white line in 1 millimeter. The first number on the chart. This is number 11. So you have 11 line in 1 millimeter. So the line is very small, very thin. And we have 2 images. These 2 images are scanned at 600 dpi. So you can see it zoom in a lot, so you can see the size of the pixel here and this one. They have the same size. They are both scanned at 600 dpi. You have 600 pixels per inch. But on this image, you cannot see the line, and here you can clearly see the line. So that means the difference is not in the sampling frequency, it is the dpi. The difference is in the efficiency. You have 2 scanners, one scanning at 600 dpi, the other one is also scanning at 600 dpi, but here you can see nothing, and here you have a good image. That means when you scan at 600 dpi or 300 dpi, you have to check if your efficiency is good or not. It's not enough to say I scan at 600, it will be okay. You don't know. And so from this chart, I can only see if it is good or not. I cannot get any number. I can just guess that here the efficiency is very good because you can see that 1 pixel has the same width than 1 line. 1 pixel gives only 1 value. So you cannot describe 2 lines with 1 pixel. So if the lines were smaller, you cannot see them because you will have 2 lines in 1 pixel, you have something gray. So the maximum I can do at 600 dpi is to look at this line because they are the same width, same size as my pixel. And you can notice that here you can see the line clearly because the pixel is in front of the line. And here you don't see it so much because the pixel now has shifted and is between 2 lines. So the pixel can see the half of the black line and the half of the white line. So it's something gray, only 1 value. So this works only when the pixels are in front of the line. That's why sometimes we put the chart a little bit like this to have all the possibility. So here I can just say that this scanner is not good. This one is okay, but that's all I know. If I scan at 300 dpi, so that make about 12 pixels per millimeter. That make about 6 pair of pixels per millimeter, so I will be able to see, so on the chart there is not 5.6, 5.9, so there is 5.6. So I should be able to see the line at 5.6 on the chart. If I can see them, that's good. If not, there's something wrong. At 400 dpi, I have to look at 8 pair of lines per millimeter. If I can see this line, that means the focus scanner is okay. If I cannot see them, if I can see only this one, for example, that's not very good. And if you go to 600 dpi, so you should be able to scan about 12 pair of lines per millimeter. So on the chart there is 11 and 12.5, so that's why we look at both. And we should be able to see the line here if you have a very good sharpness. So I can have an idea if my scanner is good or not, but I still don't get any number. So to get a number, I need this one. So this one is here. Can look also. So you will see nothing on this chart. All you have is the edge here, which is slanted, not straight. I mean, you have 4 edges, 2 vertical edges and 2 horizontal edges. So we will scan the chart And the edge here, for example, will be between 2 pixels. If I go lower, it will be in the middle of 1 pixel. I will have all the possibility. The edge will be in the middle of pixel on 1/3, 1/4, and so on. So I will give this image to software, and this software will make an analysis of this edge and will give the frequency response of the scanner from this edge. So it's a fast Fourier transform. It's a mathematical transformation that from the edge, if the edge is very sharp or not in the image, it will say the frequency is like this or like that. So here what do I have? I have the contrast, and this is the frequency. So here I'm scanning at 300 dpi. The maximum frequency I can get is a little bit less than 6. Okay, and on this scanner, what I will look at the 10% contrast, which is supposed to be the minimum I can see. And here I can see that at 10% contrast, the value is about 5.3. And it's not easy to remember 5.3 compared to 5.9, because if I'm scanning at 400 dpi, the number will be different. So it is easier to look at the percentage. So you divide 5.3 by the maximum I can get at this frequency, which is 5.9, and I get 90% efficiency. So I'm nearly at the maximum, but it's still very good. And you can see that in the horizontal direction, you have, so this is vertical direction and horizontal direction. I have about the same value, not exactly, but about the same value. So if I wanted to have more than 80% efficiency, this one is okay. If I wanted more than 90%, it is nearly okay, but not completely in this direction. And there is another number that can be interesting, is this one. It's a value at 50% contrast, which is here 2.3, because this will describe what we can see if we zoom in a lot in the image. It's a small detail. So the smallest detail we can get in the image, but when you look at the image at 100%, you don't see it, it's too small. You don't see it so much. You will more notice the contrast in this area, in the low frequency, when you look at the image at 100% zoom. And that's why it's also interesting to have this number here. So how much do I get for 50% contrast, and how much do I get for 10% contrast? We cannot describe the whole curve, so we just take 2 points. That's it. And this will give me some number. So I can be able to say this scanner is good or not good, just looking at the number. So it doesn't depend again on who makes the test, on which screen you do that, how much you zoom in, and so on and so on. That's what we want to do. And this curve is given for green, and blue, but usually we just use the luminance, because if not, it will be too complex. So at 400 dpi, you have the same kind of curve. So here we have 100 efficiency, okay? At 600 dpi, it's the same. If you have a good scanner, you should reach close to 100. And this is a sample which is not so good. So I don't know if you can see from where you are. The efficiency is about 60, 70. And you can see the curve is dropping very fast. The limit is here, so it should be like this. A straight curve from here to a little bit above that. And here it's dropping too much. So that means the scanner is not very good. The efficiency is 70. This image is made at 600 dpi. And if you look at the number, you can get about 8 pair of line per millimeter, which is a percentage between, I mean, if you take 60% of 600 dpi, you get about 8 pair of line. Usually it's not considered as a good scanner, because if you are scanning at 600 dpi and you get only 8 pair of line, 8 pair of line is what you can get at 600 dpi with a good one. So it's logical, if you scan at 600 dpi, the image size is twice the size of the 400 dpi image. So why scanning at 600 dpi to get the same resolution, same detail, than scanning at 400 dpi with a good scanner? That is why most of the time in the standard you will see that the limit is about 70%. If you are lower than 70%, the scanner will definitively be bad. So it can be the scanner which is not good. It can also be the focus adjustment which is not good. So you have to check. But at least you know what you are doing. If I show you, any question on this? No? So that's the main, the main criteria we'll have to check is the color and the tone scale with a number, and this one, and the resolution.
I'm sorry.
Sorry, yeah?
This will need to be checked before purchasing the...
Yeah.
Because
so
then it is
exactly, yeah. All we are doing now can be used before buying a scanner to check what is possible with the scanner, and also once you buy the scanner, when you have a scanner, to know when you can get with your scanner, and to check if your scanner is correctly calibrated. So we'll see later, but in you heard about the Metamorphose standard? It's in Holland. It's part of a digitalization project, and when they want to apply Metamorphose, they have to check everything, all that, in the morning, in the afternoon, before scanning. That means, by this way, they are sure that the color is right, the sharpness is right, the lighting uniformity is right, and everything. So, in the morning, in the afternoon, very important. Okay, so if you compare these two images, I guess you prefer the right one, obviously. This one is an image without any sharpening. This one, it's the same, but with some sharpening applied. So sharpening is the image processing that will amplify the high frequency. These are the curves of these two images. So this one is what you are looking for usually when you make the test. That is a straight line finishing about a little bit more than 10% at the limit frequency. This one would get 5G4 star, for example. So the best curve you can get. This one is from the same image, but we have applied some sharpening. So it has amplified not the very high frequency, you see, but the middle frequency. And that's why we prefer this image, because there is more contrast, it's better. But when you apply sharpening, it's good to check what you are doing, not only by eye like that, because you could miss something. Here the sharpening is okay. I mean, you see the curve doesn't go higher than 1, which is good. If you go higher than 1, you will finish by having a white border around the letter. And this is not very good. So sharpening can be applied. It's not forbidden. It's better to keep this image as a master image, because from this image we can go to this one. You cannot go do the opposite. Sorry, but it should not be too strong. And this chart analysis is a good way to check how much you are playing. Same on this one. You will probably think that this one is more sharp than this one. If you compare especially this line here, this one there is more contrast, it's more visible. But if you zoom in here you can see the lines, here you cannot. Okay, so which image is the best? This one is much better than this one. Yeah?
The problem we always have people order scans and they say like, oh, the image isn't sharp when I do the same with my small camera on the cell phone. It's much better than your scans.
Yeah, cell phone will apply a lot of things. So if you check the curve of these two images, The blue one is a curve like this one. I mean, I would say a good one, good curve, maybe a little bit low here, but it's not a real curve, by the way. But okay. And this one, you can see, so the high frequency are not there, so that's why you cannot see the detail. It is dropping too fast. Should be here at this frequency you have no more contrast, so no more signal. And the sharpening which is applied is probably too much. It's going more than 1, and that's why you have this effect here. You see around the black line, you have a white shadow. White. It's because of this sharpening which is too strong. Okay, so I mean, really we have to be careful on that. You can apply sharpening, but it's good to check the result on this kind of curve. And not just look at the image like this and say this one is better. When you adjust like this, just looking at the image, if you don't zoom in, you may think it's good, and in fact it is not. And again, it's too late. When you get this image, you cannot come back to this one. From this one, I can have something looking like this one, but still having some detail. And I come back to my lens resolution. Just I want you not to be confused between these two curves. They are a little bit different. Here you have the contrast depending on the frequency. So small detail, large detail. Here the curve of the lens is given in the middle of the image, on the edge of the image. And the frequency is just between these two curves. This is low frequency, this is higher frequency. And we can see here why this lens is not very good, because at this frequency, which is not so high by the way, we already have only 10% contrast, and we saw that 10% contrast is the limit we have to reach. So this lens, you should use only maybe this part of the lens. So you should not scan too much large object with this kind of lens. So any question on that? So sharpening again is not forbidden. Usually it is not applied when we make the test, because it can change the numbers. If you apply it, you have to check if it is correctly applied. Lighting uniformity is very simple. You scan something white, for example, you check the value in the middle, in the corner, you compare, and they should be about the same. Not a big issue with that. Noise. What is noise inside the image? If you scan a patch like this one, can be white, gray, or black, you should get the same value on the patch. But if you check here, on this black patch, if you check the histogram with Photoshop, you can see that the average value is about 14, but there is some variation here. And the standard deviation, that is the average difference, is about 3. That means the noise will be said, we have a 3 level of noise in this image. And this comes from the electronics, because we are amplifying and so on. And when we make the tests on this kind of chart, you have here, these are the dark patches, and you have the white patches. So you can see that the dark patches, in the dark patches you have more noise. Do you know why? Why would you get more noise in the dark patches than in the white one? It's always like that. No, it's because of the gamma correction we applied. You remember at the beginning, to get this gray level in the middle, because the camera is not looking as we are, so we have to amplify all the dark area, and amplifying the dark area will also amplify the noise. So usually you will always have more noise in the dark area. But on this sample, I have suddenly here, between these two patches, this one has more noise. Do you know also what could make that? Here it's not the gamma correction. I'm in the white area. It's not from this image, and it's not from another image I will show you. Not from here, but there is, on one patch there is more noise. No? It is simply a dust. That's very common. When you're scanning with a glass plate, you know, you always have dust at the top, at the bottom of the glass, on the chart. So you will have very often this effect. And you know, it's quite small. It's a small dust. It's not very dark compared to that, but it's enough to make, it's still under the tolerances, but it's higher. So sometimes if you have bigger dust, you will be outside of the tolerances just because of that. So it's not a big issue. But you have to be aware of that, of course. Going with the noise, you have the dynamic range. Dynamic range, what is it? It's a range of contrast you can scan. It is a range of density. We talked about density at the beginning. So it goes from the maximum density, so the darkest one, to the minimum density. The minimum density usually is always a white patch. So you calibrate your scanner to be able to scan that. And the maximum density, to know how much you can go, you just look at the noise level. You scan something darker and darker, and when the noise level is about the same level as the signal, that means you have to stop. If you have more noise than signal, it's not good. So as long as you know the noise level, you know the dynamic range you can scan. So the less noise you have, the more density you can scan. So it's usually not a problem with this kind of chart because the density is not very high. On this one, it is going up to 5 or something. So it's a better density. Dynamic range is usually not a big problem on opaque document, reflective document. It will be more problem for transparent document, where the dynamic range is much higher. You know, at the beginning we talked about dynamic range. Density, here we have density 1.5. If you scan something darker painting, you can go to 2 to 5. Going more than 2.5 is difficult. I don't know any chart going more than 2.5. After it's when you scan something transparent, you can have a very high contrast, and you can go up to 4 sometimes on some film. And now we can have a look at that, or maybe we can make a break. It's time for a break. So after the break, we'll have to look at the standard. How to use a chart, which chart we can use, how to use them, how to calibrate the scanner, and how to make the quality control. So on the screen, and in the afternoon we do it in real life. Okay. And if you have any question, again, ask.